As electronic devices become faster, smaller, and denser, it gets harder to keep them cool. A 10-degree rise in temperature can impact the performance and reliability of an integrated circuit, and can lead to system-wide problems. Engineers need to manage the heat produced by their designs, or risk seeing them fail in the field. Simulation tools from ANSYS can predict the thermal performance of a system, including chips, packages, and boards, and detect problems before a product goes to market. To accurately determine the power integrity of a design, it's critical to consider the interactions between the chip, package, and system in an integrated environment. With ANSYS SI-Wave and RedHawk, you can follow a unique chip package system, or CPS, analysis methodology, coupled with ANSYS IcePack for thermal simulation. You can also combine them with ANSYS Mechanical to simulate heat-induced deformation. As an example, we'll use the layout of the Intel Galileo board. It's based on the Quark SoC X1000. This is a low-powered chip, but it can be used in harsh industrial environments at high temperatures. Empowered by the CPS technique and thermal analysis tools from ANSYS, you can analyze and optimize a PCB like this in an integrated system-level environment. In an electronic system, integrated circuits generate high-speed electrical signals and produce most of the heat. ANSYS RedHawk can analyze the power and ground networks in an IC and produce simulation models for package and board-level power integrity simulations. Miniaturization and cost considerations have also led to decreased layer counts. To boost PCB reliability, adopt a seamless CPS methodology. You can pass models directly between RedHawk and analysis tools like SI-Wave. For example, you can easily import Apache CPM plog files as shown here. SI-Wave automatically matches the chip bump locations in the CPM model to the corresponding pads on the board. This saves the user time and prevents error by eliminating the need to manually make hundreds of connections. You can easily toggle the part name selector to review the connections established. With power distribution models that span the chip, package, and board, you can perform signal integrity and radiation simulations in SI-Wave. These near-field plots show where radiated emissions are coming from the board, and at what frequencies they're a problem. System designs often involve a trade-off between cooling and electromagnetic shielding, so you need an integrated system that can look at both effects. Turning now to the thermal analysis in SI-Wave, you can configure and run a DCIR drop simulation for calculating the ohmic power loss. SI-Wave flow wizards make it very easy to set up the analysis. You can assign voltage sources to model the VRM and current sinks to represent the main SoC. You can select the nets to analyze and define multiple voltage and current source excitations. The SI-Wave design flow also allows you to invoke the IcePack solver-on-demand capability for thermal analysis directly after completing the DCIR analysis. The DC simulation is very fast. It takes less than a minute to create a finite element mesh, analyze it, and adaptively refine the mesh to accurately represent the DC current distribution in the board. SI-Wave can also create a DCIR sign-off report. The power tree shows the actual current drawn by the individual components on the PCB. Here you see the voltage and current plots. Current is drawn from the VRM and flows through the lowest resistance path in the power plane to the chip. The current returns through the ground plane. The I2R power losses from SI-Wave serve as a starting point for the thermal analysis. Power maps calculated from the DCIR analysis are transmitted to IcePack. The rectangular thermal cells represent the power being dissipated on different layers. The IcePack simulation setup in SI-Wave lets you define the worst-case thermal design power for each component. Here we've entered the 2.2 watt power dissipation for the Quark SoC X1000 from the Intel datasheet. You can also assign heat sinks to all or some of the components. In this case, we add them to the VRM and the SoC. From SI-Wave DC, you can invoke the IcePack solver very easily. When you initiate the solution, IcePack is launched in batch mode. IcePack imports the design, applies the power map from SI-Wave, and then performs a thermal simulation using the industry-leading ANSYS Fluent CFD engine. You can use SI-Wave to visualize the temperature profile computed by IcePack. Here we see that the hotspots are around the VRM and the Quark SoC. For more detailed investigations, you can also open the project in IcePack to see the environment surrounding the board. You can examine the results with contour and vector plots that represent the range of temperatures, and particle displays that show the airflow. These simulations let you verify that temperatures across the different components on the PCB do not exceed their design limits. Using the results from IcePack, you can also do a structural simulation to analyze the heat-induced deformation of the PCB. The process is simple. Import the Galileo board into ANSYS Mechanical from the SpaceClaim modeler and define its material properties. The trace metal data on the board is processed and mapped onto a finite element mesh for the mechanical solver. This plot in ANSYS Mechanical shows the metal density across the board. This will determine the spatial distribution of the mechanical material parameters used in the finite element simulation. Here we have analyzed the mechanical consequences of cooling the board down. Contour plots of the z-direction deformations show the PCB has been warped at the center. Since there is more copper underneath the top layer, the board is bowing downward. You can also see high levels of stress due to contraction. These effects could potentially contribute to delamination or breakage in the component solder joints. In order to beat the electronic heat, you need to adopt a cool, refreshing chip package system design methodology involving ANSYS RedHawk, SI-Wave, and IcePack. Pour ANSYS Mechanical into the mix, and in the end you'll establish the confidence that your product will perform as expected. Until next time, goodbye.